Okay, so it's recording now. So, right, I'll ask everyone if you could mute your while I'm talking. But if you do want to say something, just unmute yourself and say something. That'll be the easiest way to do it. I'm more than happy to take questions and respond. It's quite a informal, talk. It's more of a discussion, and the talk is just to kind of get the ideas kind of going. I think that you can see me in the screen because I'm talking, although I see something different. So, yeah, just interrupt if things are not going well or if you have any questions, and I'll begin. So, so the talk this evening is about this work I've been doing on the concept of frugal coordination, and I'm going to kind of explain what that is, and then I'm going to show you this model that I've been working on. That's actually a graph-based agent model. So it's a model that it exists only as a proof of concept at the moment, but it's written in Cypher, which is the query language for a graph database called Neo4j. Although there are some other databases that also use the same language, because Neo4j is quite a big player in this market, and others are kind of piggybacking on him. So anyway, this is what the talk's about. And there's always art in my talks by James Robert White, because he's somebody that I've collaborated with for years, and he just kind of livens up my slides a bit, and I really like what he does. So if you have any questions about James's work as well afterwards in the questions, we'll have a question section, and I'm more than happy to discuss James's work, of which you see a photo right there. So, so the agenda is, first I'm going to talk about this concept of frugal coordination. And I'm going to talk about why I think it's actually a universal sort of economic principle. So when we talk about economics, we normally talk about, human social affairs and the economy of money going round. But I think we need to think wider than that. And obviously economists do think wider than that, and they apply their ideas to biology, and that's been going on for decades. But I do think that there is this interesting concept of frugal coordination, and it's interesting enough to deserve its own kind of topic and concept to be discussed in its own right. So after I've introduced that topic and talked about why I think it's so universal, I'm going to then talk about why I'm building a graph-based agent model to capture this process and these kind of this principle and the dynamics and of agents coordinating frugally with the environment and each other. So that's it. That's the agenda, really. After the end of the talk, there'll be more time for more questions. So if you prefer to have a question at the end, there'll be time to, hopefully plenty of time to discuss the questions and discuss things further after the main talk. So first up, what is this concept of frugal coordination, and why do I think it's a universal kind of principle? Right, so to begin with, in the kind of the science of cybernetics, which also has a long history, there's this principle called the Law of Requisite Variety, which is quite an old-fashioned term for what I think is quite a simple and intuitive idea, originated by Ashby. And the idea is that if you want to control, bad news. So my internet is maybe playing up, but the idea is that if you want control of your environment as an agent, then it requires, if the environment is of a certain level of complexity, then the agent also requires a certain level of complexity in order to match, if you like, and then control the environment itself. And so, roughly speaking, that's just the idea, right? And it's quite an intuitive idea that a really simple agent can't control a really complex process. And you see this, in engineering with lots of regulating systems and so on. The principle I want to introduce is this idea of frugal coordination. So it's just saying that although agents need a certain level of complexity to control a complex environment, according to Ashby, they also are very often forced to reduce the cost of internal states and reduce the complexity internally. And the reason is things that I'll discuss in more detail. But essentially, they need to control that cost because it's often a very high cost. That complexity is often something they can't afford. And one of the reasons they can't afford it is very often in nature there are rivals who can propagate and evolve and be successful because they can reproduce more quickly because they have more energy to do so. But it's also the same in economics, where they're more agile rivals that are simpler and have less internal complexity, can move more quickly in markets and so on. And you get this concept of agility from that. You might be able to hear something in the background, which is the shopping being delivered, but it'll be dealt with. The other principle that I want to include in this is actually a different principle, and it's the idea that complexity is dynamic. So there's lots of different ways of thinking about complexity that are useful for different kinds of things that you're interested in. But the kind of complexity I'm interested in is complexity as a dynamic quantity. So I'm interested in complexity as something that's changing in the environment on every time scale. And this is not maybe an idea that we're that familiar with in complexity science. We talk about dynamics, but we don't talk about complexity dynamics that much, as far as I'm aware. But this is what I want to focus on: the idea that every second, every hour, every day, and every month, the level of complexity in your environment is changing in cycles or progressing in a certain direction, and that this is affecting the agents that are trying to coordinate frugally, but sufficiently well, in the environment. So this idea is that environments are changing in complexity and agents are pressured to follow and track that. And this leads to all kinds of interesting results and behavior that we can see. So the first idea is that, the increase in the complexity of the environment will often force, because of Ashby's law, the agent to increase in its complexity. So that's one way that the agent has to track the environment's complexity. Secondly, if the environment gets simpler, or the requisite internal states is less by Ashby, then the environment is often, or the rivals, in fact, of that agent often force that agent to reduce in complexity where possible. And that's by the frugal coordination principle. And then finally, the dynamic principle says that this is happening on every time scale, right, in nature and across different domains, which is what the domains of what I'm going to talk about next. So this has all been very abstract, and now I'm going to talk about some specific domains where we see these patterns. And the idea, of course, is complexity science as a general method is to look across domains, and that's what I've been doing. So that's what I'm going to do next, is look at, is this a kind of a principle that works in different domains? So as an example of a kind of long-term timescale, we have this concept of perception having to be frugal because perception has evolved. And an example of this is the jewel beetle, which is discussed by this researcher into perception, Donald Hoffman. And this jewel beetle is trying to mate with this beer bottle. And the reason it's trying to mate with this beer bottle is because the beer bottle is the same color and similar kind of texture apparently to a female jewel beetle. But you'll notice that the male jewel beetle is much smaller than the bottle. And the reason this hasn't been noticed by the male is that it doesn't have the ability to distinguish between the size of the beer bottle, even though it's so different to the size of a female jewel beetle. And this actually causes a problem in Australia because Australian men and women are chucking these empty beer bottles out the window of their cars as they're driving. And these Australian jewel beetles are driven to kind of just mate with them until, unfortunately, they die. So it's actually a bit of a kind of ecological problem. And Donald Hoffman discusses this idea because he wants to show that perception, including our perception, has to have evolved. And because it has to have evolved, because it's a product of evolution, it also will have had to be frugal, because as he shows in his simulations, if you have a more complex, sophisticated dual beetle that can detect the size of the object it's trying to mate with, and so doesn't mate with a beer bottle, it costs the agent, this dual beetle, a lot in terms of resources to maintain that ability. So it has to, and it can't really afford to do that, because it has to use that energy for other things like procreating. So simpler rivals will drive out the more complex dual beetle. And this is Donald Hoffman's work, and this is what he's started with for his research. And it's an example of a very slow moving dynamic, more like a geological timescale, where the collision is what's happened, is that the environment has suddenly become more complex for this dual beetle, because there are now these beer bottles here, which they weren't there before. And the dual beetle cannot match the increase in complexity that Ashby says you need to control the environment. So this is an example of a collision where the agent can't match it. And that's one of the dynamics we're interested in. And the reason it can't match it is because it's become too simple, if you like. So there's limits to the agents being able to track changes in complexity, a bit like temperature. So I'll explain more about that idea as we go on. A totally different time scale, but also with perception, we have this concept of habituation. And so habituation is, a commonplace in kind of neurology, but not just in neurology of human beings, but also in all animals, in even cells, when their signal transduction systems, I believe, are habituating. And what this means is that if a new stimulus enters the environment, then there's an increase in the resources used by the agent to kind of assess what to do about that new thing. They might have a choice to make. They might need to eliminate it. They might need to run away from it. But if that new stimulus that appears in the environment, this new thing, doesn't seem to have any consequences, then the agent will quite quickly habituate, and then it'll step down, if you like, and de-escalate its responses, and then just start to ignore that thing. And this pattern is ubiquitous, and it's on a fast time scale, obviously, not the evolutionary time scale we were just talking about, but it's also to do with perception, and it's also to do with this coordination dynamic, because the reason we think habituation exists is to free up resources for other kind of processes in a perceptual system, such as associative learning and reinforcement and so on. So you don't want to waste, you want to be able to react. If the environment becomes more complex, the first thing you do is escalate. So you match the complexity, which is the new stimulus. And then what happens is you realize this is a false change in complexity, if you like. And so the complexity then returns, then reduces, if you like, to a lower level, and the agent then tracks that as well. And upon kind of learning, if you like, that the environment is not really more complex, it returns to its former kind of level of complexity, which is more frugal. So this has been called the simplest, most universal form of learning, as fundamental a characteristic of life as DNA. So you find it everywhere in nature. Okay, so now I'm going to go back to the very slow ecological evolutionary change, but I'm not going to talk about perceptual systems such as the dual beetle or habituation. I'm going to talk about natural selection as a whole. So if you look at the whole process of evolution, it exhibits this frugal coordination principle, because all agents, the whole organism, is under pressure to track changes in the complexity of the environment, because that's the way natural selection works. It's not smart enough, if you like, to realize that, well, what I was going to say is it leads to problems. This leads to collisions on a kind of ecological or an evolutionary scale for organisms. So an example of what I mean, this is a paper that sets out to measure the rate of mutations in this yeast, which are beneficial. And in the paper, they report that the rate of beneficial mutations in this yeast was higher than they expected. But if you go to the protocol in the paper, they explain, and please tell me if my internet is going to be a problem because it's warning me that it might be. But if you look at the protocol in this paper, they explain that a lot of the mutations that they're classifying as beneficial that happened in the lab when they tracked, which yeast were doing better by mutating in their, their Petri dishes, wherever, in the growth medium in the lab, were actually not really beneficial. The reason is that they were only beneficial because the yeast is in a simple environment, which is the lab Petri dish. And in the lab Petri dish, there are metabolic pathways that, so I'm just going to check my chat. Right, so I'm not, okay. So yeah. So we'll see. Well, I'll press on, but I realize that you might not be able to follow everything that I'm saying, so unfortunately. So there are metabolic pathways that are not needed in the lab. So if you have a mutation that...
Adam, if you could switch off your video.
Switch off the video?
That would probably fix it.
Okay. Yeah. Okay, so I'll plow on. If you, yeah, the mutations that actually occurred, were beneficial in the lab, but disabled metabolic pathways that would be needed in the real environment. But because the things they were needed for are not situations that occur in the Petri dish, these yeast were with that mutation were actually growing faster than the more complex yeast that retained that complexity. And so what you see is that natural selection has this problem with tracking complexity, because you end up losing information. And so one of the outstanding questions in evolutionary biology is, how do organisms retain information that they actually need when they actually enter into a simpler environment? Because simplicity is actually an existential threat, because you can lose genetic information, and then when the environment becomes more complex again, you're in big trouble. And some very interesting questions emerge from modeling these sorts of dynamics about how it could be that nature deals with this problem. Finally, I'm going to talk about economics. So I've already mentioned that kind of at an organizational level, we're used to the idea of kind of like companies becoming too large to be able to move quickly, and in terms of opportunities and entrepreneurial entrepreneurial kind of context, and so that's clear that we have a similar kind of an analogy with this threat of becoming too complex, and if the environment is demanding simplicity, it either forces you to kind of become simpler, or if you can't, you can get overtaken by rivals that are moving more quickly, because it's easier for them to do so because they're smaller and simpler. You also have dynamics in terms of cycles, business cycles they called, of boom and bust. And I think that these dynamics are also can also be modeled in terms of complexity. So an example is a model by Hyman Minsky, which has been revived after the 2008 crash. And his model that he developed in the 70s and earlier modeled the idea that the financial system is inherently unstable, because during times of a boom, the investors he claimed they became euphoric, which doesn't really make sense to me, but they take more and more risks because their rivals are also taking more and more risks. And then regulations are also kind of lobbied to be removed, even though those regulations were to protect against, risks of crashes. And you see this pattern, and it kind of happened in 2008, that although the financial products being dealt with were very complex, such as these CDOs, the agents were behaving in a very simple way and had been for some time, because they were just following things like the ratings agencies' classification of these products. And they didn't have, there was a collision because they weren't then tracking the true complexity of what they were doing anymore. So I'll be basically arguing that economics can be understood in terms of these complexity cycles, and that it makes more sense than some of these other models. And the advantages of looking like this is that you look across different domains and see the actual pattern without overfitting to a particular domain. So you don't need to talk about euphoria. You can just talk about complexity and the way agents have to try and track it. So all of that discussion is just kind of leading to this initial claim, the original claim I make, which is that complexity dynamics, or this kind of frugal coordination dynamics, are ubiquitous in nature in economics. And so you can call it, I've come up with this term, Ubiquinonic Principle. So, that's the idea of what it is I want to model. I want to think of complexity as a dynamic thing and agents trying to track it. And I think you see it everywhere. So this has led me to look at graph-based models. And essentially, the reason to look at graphs is that, first of all, graphs are known to be good at representing the beliefs of agents. So it's a very economical way of representing what agents believe, and also what they don't believe, even though something else may be the case. And so it's good for me because I'm trying to model where agents are kind of too simple to understand the environment that they're in. So I think graphs are a good choice for that reason. Another reason is that they also seem to be quite good at modeling difficult abstract relationships. And there's a guy named Judea Pearl who's come up with what he calls causal calculus. And he wasn't the originator of this initially, but he's revived it and developed it. And he uses graphs to actually model the relationship between causation and correlation. And he does statistics with information about causality built into the statistics. And he uses graphs to define the causal relationships, as well as marrying that to the statistical information. So it's interesting what you can do with graphs, basically. So that's the first part of the talk. I've talked about frugal coordination, why I think it's a kind of ubiquinonic principle. In the next part of the talk, I'm going to attempt to show you how a graph-based agent model can be used to capture these dynamics. But I will need the video to do this because they're graphs. So let me put the video back, and let's see if we survive the experience. Right. So if you bear with me. The model that I'm working with has three classes of vertex, which is just another word for node. I use them interchangeably. So there are three types of node in this graph model. The first one is agents. So obviously that's quite self-explanatory. Those are the agents whose behavior you're trying to model that are operating in the environment. In this type of graph, they follow or subscribe to utilities. Now, utilities are a bit more of an abstract concept. So they kind of can be part of the way the agent's brain works or what it does, but they can also be something almost kind of external, like a notepad or a website could be a utility, or a task could be a utility. So it's a very flexible concept, but it does mean something. It means this is something that it costs the agent to subscribe to get the benefit of. But if it subscribes to it, it can get the benefit of that utility. So then the third type of node in the graph is contexts, and they represent the environment. And utilities follow context because utilities are moved around and we compute where the utilities are pointing to. In other words, where they're leading the agent to that's following them. And using this idea, we can model things like that jewel beetle. So it can have a utility that is detect brown dimpled objects that might be female jewel beetles, and it can have another utility, which is check the size of these brown dimpled objects, or just check the size of objects generally. And we see that if you subscribe, if the jewel beetle subscribes to both those utilities, there's a cost, there's a subscription cost. And so it might make sense for the agent not to do that, which seems to be the case for the way that the jewel beetle has evolved. So in this example, I'm showing you that there's an agent, and the agent likes to have, I'm just going to check what's going on. Yeah, I should still be able to share screen. Okay. Okay. So you can still see the screen apparently, which is good. Yeah, so the edge that I've highlighted in blue here. So first of all, this is an agent that is interested in having dinner with people. And essentially in this scenario, there are two separate utilities that we've modeled. One is having dinner with Monica, and another one is having dinner with Teresa. And in this scenario, they're both achieved by going to the same restaurant. Why? Because you're all having a meal together. So these two utilities have a switching cost, which is 0. And that means that it derives that from them pointing to the same context. And it means that the agent gets one. If it follows one, it gets the other for free. And so this is a description of a simple environment. So the agent doesn't have to choose between these two utilities. They're kind of compressed together in one context, and one flows from having the other. So in that scenario, it might be cheaper for the agent merely to track what the dinner arrangements with one of these people, right? Because it costs otherwise to try and coordinate with both of them. But if Teresa always shows up where Monica's eating, then I don't need to worry about Teresa because the switching cost is 0. And so in the graph database, we can do a query that tells us, the switching cost is 0. So you get the utility B if you follow utility A. And therefore, the agent may be updated to become simpler to match this simple environment. But what happens if you can't achieve two utilities, you can't kill two birds with one stone, and if you're making arrangements with Monica, she wants to go to a restaurant outside of London. If you want a meal with Teresa, she wants to go to a restaurant in London somewhere. And so we show this with the edge with a switching cost of 10. And if the agent can't afford to do both, if he hasn't got the resources to do both, and it has to choose between them, then the fact that it has to escalate because the environment is now more complex is something the agent knows because it's subscribed to both of these utilities. And you can think of it as almost like following a herd or something. The utilities are things that the agent is following. And when the two things the agent is following go in different directions, the world is more complex and the agent has to do something. But if the agent had become more simple, right, and is only following one, now it doesn't get one from following the other, and also doesn't even realize that there was a choice to be made, right? So it doesn't follow the complexity of the environment, and it may have a kind of a disutility as a result. It might make the wrong choice through not making any choice. And this is what we might think of as potentially a collision, where we would model the agent as being now too simple. And it's all emerged from the dynamics that are happening with the agent matching the changes in the complexity of the environment. Because if Monica and Teresa always have dinner together, the environment has been very simple for a long time. And so the agent stopped tracking what Teresa was happening. And then one day Teresa didn't show up. And so this is how we can map these things quite naturally in a graph. So in this example, I just want to show you that what you would do in the simulation is that you decide where to draw these utilities as arrows. So you'd say, okay, utility A is good food. Where do I go for good food? And you would compute utility A, and you'd find out that in one context, there's definitely good food in this restaurant. In another context, actually, the food is okay, but it's nowhere near as good as that one. And so you would draw an arrow to the restaurant in central London from utility A to that context. You might do the same thing for friendly staff and get something else. And if you're an agent and you're following these two utilities, the situation is complex because you have to choose between these two. But there's something missing from that simple model, which, as good as it is, there's also a contribution of other utilities that are indifferent to the choice. And so you'd have these other utilities, like say, I'm going with the same person to either restaurant. And actually, that simplifies, that's on the simple side of the equation. So what you would do, in fact, in the graph is you'd summarize these different utilities, some of which add to the simplicity. So you're indifferent as to the choice. So it's not really a choice isn't necessary. And some of which make the situation more complex. And the weighting between the two, so how much is good food worth versus good company, describes how complex, excuse me, how complex the environment is for the agent. So that's just more of a technical point, but it's just showing you how in practice this kind of thing would work. So now I'm going to kind of just do a quick demo, and it's not really a demo of the code. It's just to show you a few more examples, but using Neo4j. And yeah, it's a scalable database. It has some kind of an interesting subscription thing where you can use it for free in startups, apparently, if you have less than 50 employees. So it's quite interesting as to see how you would scale this kind of thing up. And so now I'm going to just do the demo and show you a little bit more. So I have some scripts here to initialize the database, and then I can show you a graph that I've created, a kind of proof of concept, and hopefully you can read this. But essentially, in this example, we have what I'm calling a weather agent, and it's basically Jeff is somebody who likes to sunbathe, and in this scenario, he just has to choose between whether he wants to sunbathe in the park or whether he wants to go home. And he's following the two utilities. The main one is get vitamin D because he's sunbathing and avoid the rain. You can read the description down here when I hover over it. And we see here that there's another utility, which is avoid getting sunburn. And there's a switching cost between them. There's an edge, which has a cost down here. You'll see it of 0 at the moment, which means he gets one from the other because they're pointing to the same context. So given that they're pointing to the same context, we derive the switching cost. So in this scenario, life is quite simple, and we can run a simple graph matching query to decide whether Jeff whether he realizes whether he needs to make a choice, and in fact whether he does need to make a choice. And that returns no records because he doesn't need to make a choice, because there's no the graph pattern is not one which shows that a choice is necessary. So there's no escalation needed because the environment is not complex. But let's say the environment increases in complexity, which is what I've just done there. I've just updated the graph. So when I refresh this, now we're in a situation where he's been in the park for a while, let's say, and now avoiding sunburn is only achieved by going home. But obviously to get more vitamin D, he should stay in the park. And so the switching cost is also updated to say 20. So he has to decide between the two of these. Now, if I rerun my is a choice needed, or does he realize is a choice needed, then we see that it returns these records because this is the pattern of having to make a choice. And so what would happen is there'd be an escalation of the agent, which we would record in the graph, and we would then have him make his choice, right? So let's say that he doesn't actually follow one of these utilities. And as a result, the graph looks like this now. So he's only interested in getting vitamin D and sunbathing, and he's now not paying any attention as to whether he's going to end up getting sunburnt. So if the situation is now complex and he does need to make a choice, if I take the same query up here, which the same query here, which asks that question, this is the question: does he realize that he needs to make a choice? And it's a no, because there's no records returned, because it doesn't have the pattern where he's following this utility. So we don't complete the pattern of a choice. So we can do another query to say, would he benefit from having a choice? But this query is checking, does he realize? And so there would be a collision here and he would get sunburnt. So we can relabel this, and I can show you exactly the same diagram, just with different labels, just to illustrate how it's applied in different situations. So this might be this Jeff is now a jewel beetle. He wants to check if the brown and dimpled object is a female jewel beetle, but actually if he could check the size, he'd realize it's not a female jewel beetle, but he can't. So there's a collision. So this is kind of the pattern and general pattern of a collision. And just to finish the idea off really in terms of different examples, you can think of this is now a software project, and you can think of iteratively working through some requirements and then us updating the complexity of the requirements. And when I say complexity here, I mean, if Jeff is working on this requirement and he's following the JIRA ticket, which is that utility, which costs something to do, obviously checking the JIRA ticket. And the JIRA ticket says, this is what you should do. This is the requirement first option. But if he talked to the business user at this point, he'd realize the JIRA ticket might be wrong, and it might be this option he should be choosing. Now, if he's not subscribing to the business user, he's not talking to them because it costs something to do that, there's going to be a collision. But if most of the time these two are always pointing in the same direction, why should he bother subscribing here? And that's kind of one of the essential ideas. Now, I have some other examples that are more complex than this, but I want to focus on the fundamentals really. So that's what I want to. I think that's all I'm gonna show you, just to give you a flavor of the idea. I don't know how we're doing. We're doing okay for time. Actually, quite under it, which is good. So I've explained the concept of frugal coordination, and I've given you this demo. I've talked about the ideas, and there's all these different research questions. There's a huge list of things that you'd want to do. You'd want to build a full simulation system. You want to include aggregates of these kind of local graph cliques. You would, in one of the scenarios I haven't explained there, but I've done a little mock-up. The agents could follow each other, right? So they derive utilities from each other, and then you get the same pattern, but just slightly more extended, where agents are following other agents, and then that can either lead to collisions or recognition that there is a collision. You want to model the ways that the pressure to follow the complexity increases or decreases, and the general strategies for agents to track that complexity change, and also to resist, following the complexity too far. As we saw in the evolutionary example of the yeast and the petri dish, how do organisms resist becoming too simple and losing information? Again, Marvin Minsky's boom and bust is another example, I think, of agents becoming too simple, tearing up regulations that would protect them from a more complex environment, for example. It could be financial regulations. So there's lots of other things to talk about here. There's lots of work to be done. But the next thing I'm going to be talking about will be the purpose of sexual reproduction. And I mean in evolutionary terms, right? So why do so many organisms choose to reproduce sexually rather than asexually? and I'll be talking about how ubiquinomic, this theory, can maybe cast a new light or a new angle on this kind of like what I think is an important topic. And you can follow me on my website, fractalagility.com, and you'll find out where and when I give this talk, because I don't know where I'm doing it yet, but I plan to do it. And I'm also on LinkedIn, and I'll be uploading this video, if it survived, onto YouTube, and you'll be able to see the details of when I'm giving more talks from there. So thanks to all these people for either contributing ideas or having good chats with me, and that's it. So the next part of the evening, we'll just have plenty of time for discussion or chatting, more questions, or whatever you want to do. So thank you very much, and I'll return you to the host.
Awesome. Thanks so much for that.
No
Adam.
problem. Yeah, I don't know how. I'll have to look at the recording for myself to know what people got, but I appreciate your messages, Dylan, telling me what's going on. I need to stop recording as well.
No worries. I mean, yeah,